In the velvet blackness of the cosmos, there are wanderers. These are not the familiar clockwork travellers of our own solar system. They are not our planets, our asteroids, or even our own comets. They are pilgrims from an unimaginable distance, emissaries from other suns. For millennia, we gazed at the heavens, believing our celestial family to be a closed, isolated system, a lonely island of gravity in an ocean of emptiness. We were wrong. The story of this revelation begins not in a grand observatory, but with the patient eye of a single man. On a late summer night in 2019, an amateur astronomer named Gennady Borisov, using a telescope he built himself, detected a faint smudge of light. It was a comet, certainly, but there was something profoundly unusual about its motion. This object was moving with a ferocious velocity far too fast to be bound by our sun. It was not in orbit. It was a visitor, screaming through our neighbourhood on a one-way trip. Astronomers around the world scrambled, turning their most powerful instruments towards this fleeting apparition, designated 2I/Borisov. It was only the second interstellar object ever detected within our solar system. The first, the enigmatic Oumuamua, had been a fleeting, tumbling enigma. But Borisov was different. It was trailing a familiar tail of gas and dust. It was an active, breathing comet, and we could analyse its very essence. What we discovered in its vaporous breath was both shocking and deeply familiar. The chemical fingerprint, the composition of its nucleus, was almost indistinguishable from the long-period comets born right here, in our own solar system. This ghost from another star system, a place we can only dream of, looked just like one of our own. This startling resemblance posed a profound question, a cosmic riddle. If this alien artifact is so similar to our own most distant objects, then what does that imply about the place they come from? It forces us to turn our gaze away from the interstellar darkness and into the deepest, coldest, most mysterious territory of our own home. It compels us to ask, what is truly lurking out there, in the profound abyss that marks the beginning of the sun's gravitational kingdom? And could it be that this celestial frontier is populated not by thousands, or even millions, but by trillions of objects, a ghostly sphere of primordial worlds that dwarfs everything we have ever known? To understand this staggering possibility, we must journey to a place no human eye has ever seen, a realm so vast and so empty that it exists more in theory than in observation. This is the domain of the Oort cloud, the great frozen shell of our solar system. It is a concept born not from a direct photograph, but from a brilliant piece of celestial detective work. The puzzle began with comets, the so-called dirty snowballs of the cosmos. For centuries we watched them appear in our skies, their glorious tails stretching across the zodiac. Some, like Halley's Comet, were predictable, returning on regular schedules. These are the short-period comets, originating from a disk of icy bodies beyond Neptune known as the Kuiper Belt. But there was another class of comet, far more mysterious. These were the long-period comets, appearing as if from nowhere, on orbits lasting thousands, or even millions of years. They arrived from all directions, not just the flat plane of the planets. They seemed to be falling in from a great, spherical reservoir of material. In the mid-20th century, a Dutch astronomer named Jan Oort contemplated a paradox. Comets are fragile. Each time they swing past the sun, they are baked by its heat, losing tons of ice and dust, their lives shortened with every passage. If they had been orbiting for the 5 billion year history of the solar system, they should have all disintegrated by now. The supply of new, pristine comets arriving from the void should have run dry eons ago. Yet, they keep coming. Oort reasoned that there must be an immense, unseen repository of these objects, a colossal refrigerated warehouse located at an extraordinary distance from the sun, where trillions of cometary nuclei lie in a state of perfect preservation, frozen at temperatures just a few degrees above absolute zero. This theoretical structure, which would come to bear his name, was the only logical explanation for the ceaseless parade of long-period comets. He proposed a ghost sphere, a halo of ancient ice surrounding our entire solar system. To grasp the scale of the Oort cloud is to confront the limits of human imagination. Let us try with an analogy. Picture our sun, not as a star but as a single grain of sand held between your fingers. On this scale, the Earth would be a microscopic speck of dust, orbiting about an inch away. Jupiter, the king of the planets, would be a slightly larger dust mote, 5 inches out. Neptune, the most distant major planet, would be a fleck of powder nearly 3 feet away. The Voyager 1 spacecraft, humanity's most distant emissary, after more than 4 decades of travel, would on this scale have journeyed just 12 feet. It is still, by any measure, deep within the Sun's immediate neighbourhood. Now, where is the Oort cloud in this model? To find its inner edge, you would have to walk from that grain of sand for 2 full miles, and to reach its outermost boundary, its wispy, tenuous frontier with interstellar space, you might have to continue walking for 50, or perhaps even 100 miles. The entire planetary system, all of history, all of human endeavour, is contained within the first few feet of a structure that is 100 miles across. It is a sphere of such incomprehensible volume that the space between each of its constituent objects is millions of miles. It is less a cloud of things and more a cloud of impossibilities, a spherical vacancy sparsely populated by frozen relics. And how many relics? Oort's initial calculations were conservative, but modern estimates are staggering. The numbers suggest that this celestial halo contains not billions, but trillions of objects larger than a kilometre in diameter. Some models push the population estimate towards 10 trillion individual worlds. This is a number so large it loses meaning. 10 trillion is more than 1,000 times the number of stars in our Milky Way galaxy. It is more than 1,000 times the number of human beings who have ever lived. If you could count one of these objects every second without stopping, it would take you more than 300,000 years to finish. This is the population of our Sun's forgotten family. These are not just inert chunks of ice. Each one is a pristine time capsule, a chemical fossil from the very dawn of our solar system. To understand their significance, we must travel back in time, 4.6 billion years. The Sun has just ignited, a newborn star surrounded by a swirling protoplanetary disk of gas and dust. In this chaotic nursery, particles of dust stick together, growing into pebbles, then boulders, then planetesimals, the building blocks of planets. Closer to the young Sun, it was too hot for ices like water, methane and ammonia to condense. Here, the rocky planets formed: Mercury, Venus, Earth and Mars. But farther out, beyond the frost line, it was cold enough for these ices to solidify. This is where the giant planets were born, gobbling up enormous quantities of gas and ice. Jupiter and Saturn swelled into colossal gas giants, while Uranus and Neptune became icy behemoths. The early solar system was not the orderly, predictable place we know today. It was a violent gravitational pinball machine. The newly formed giant planets, in a cosmic dance of shifting orbits, wreaked havoc on the remaining swarms of icy planetesimals. The gravitational influence of these titans was immense. Countless trillions of these smaller icy bodies were flung about like cosmic shrapnel. Many were thrown inwards, some delivering water and organic compounds to the young Earth, perhaps seeding our world with the very ingredients necessary for life. Many more were ejected from the solar system entirely, cast out to become interstellar wanderers, much like the object Borisov would one day become. But a vast number of them were thrown outwards, yet not with quite enough energy to escape the Sun's pull. They were lofted into immense, looping, highly eccentric orbits. Over hundreds of millions of years, the gentle, persistent nudges from the gravity of passing stars and the tidal forces of the Milky Way itself circularized and randomized their paths. Their inclinations were scrambled until they no longer occupied a flat disk. They formed a great spherical shell, a halo of frozen exiles. This is the Oort cloud, a testament to our solar system's violent birth, a repository of lost worlds. So, the answer to the question of whether there are 10 trillion objects like 2I/Borisov within our solar system is a profound and resounding yes. In fact, the truth is even more mind-altering. Borisov is not just like the objects in our Oort cloud. The objects in our Oort cloud are Borisov's long-lost siblings. They were all born from the same fundamental cosmic ingredients, in the same type of stellar nursery. The familiarity of that interstellar visitor was not a coincidence. It was a message. It told us that the processes that built our solar system are not unique. Across the galaxy, other stars are being born, surrounded by their own disks of gas and ice. Their own giant planets are forming and migrating, flinging their own planetesimals into their own distant spherical clouds. And some of those objects, trillions upon trillions of them, are inevitably cast out, sent on lonely voyages across the interstellar void. This shared heritage blurs the very definition of ours and theirs. Consider the environment where our sun was born. It did not form in isolation. Like most stars, it was born within a dense stellar cluster, a celestial crèche with hundreds or thousands of sibling stars, all packed relatively close together. In this crowded cosmic nursery, the nascent Oort clouds of these neighbouring systems would have overlapped and mingled. It is almost certain that in the chaos of those early millennia, our young sun gravitationally captured icy bodies that were originally born around another star, and in turn, our sibling stars would have stolen some of ours. This implies that our own Oort cloud is not entirely our own. It is likely a composite structure, a blended family of objects from dozens of different, long-lost solar systems. Some of the trillion comets orbiting our sun at this very moment may be true interstellar immigrants, adopted into our system billions of years ago. They are alien worlds that we can rightfully claim as part of our solar system. The object we call Borisov, then, was not so much an alien as it was a cousin, returning to a neighbourhood much like the one it left behind. Its journey gives us a glimpse into a galactic ecosystem we are only beginning to comprehend. The galaxy is not a collection of isolated islands. It is a vast interconnected network constantly exchanging material. Over billions of years, stars shed their atmospheres, supernovas explode, and comets are flung from developing solar systems. This material, rich in heavy elements and complex molecules, seeds the next generation of stars and planets. The interstellar medium is a cosmic ocean, and objects like Borisov are its plankton, drifting on the currents of galactic gravity. The existence of this colossal reservoir of primordial matter has profound implications for the story of life itself. These comets are not just ice and rock. They are packed with organic molecules, the carbon-based chemistry that forms the backbone of life. Amino acids, the building blocks of proteins, have been found in meteorites that are fragments of similar bodies. They are also incredibly rich in water ice. The very water you're made of, the oceans that cover our planet, may not have originated solely on Earth. A significant portion of it was likely delivered during an era of intense bombardment, billions of years ago by comets and asteroids flung inwards from these outer reservoirs. Each of the 10 trillion bodies in the Oort cloud is a potential chemical laboratory, a frozen ark carrying the elemental ingredients for life. When one of these objects is nudged from its stable, distant orbit, perhaps by the gravitational tug of a passing star, it begins a slow, multi-million-year fall towards the inner solar system. As it approaches the Sun, its ancient ices sublimate for the first time in 4.5 billion years. It awakens, releasing a cloud of gas and dust that contains a perfect, unaltered sample of the primordial nebula from which we were all born. By studying these long-period comets, we are, in a very real sense, performing an archaeological dig on our own origins. They are messengers from a time before planets, delivering secrets from the dawn of our world. But this raises a tantalizing and formidable challenge. How can we ever truly explore this vast hidden architecture of our own home? The distances are simply beyond human comprehension. Voyager 1, travelling at over 35,000 miles per hour, will not reach the inner edge of the Oort cloud for another 300 years. It will then take that intrepid probe approximately 30,000 years to traverse it. By the time it emerges on the other side, its power will have been dead for millennia, a silent ghost ship sailing into the interstellar sea. A dedicated mission to the Oort cloud would represent the most ambitious journey ever undertaken by humanity, a true multi-generational quest. Imagine a future spacecraft, perhaps named the Oort Sentinel or the Janus Explorer. It would need a revolutionary propulsion system, perhaps fusion rockets, or a light sail pushed by immensely powerful lasers just to shorten the travel time to centuries instead of millennia. Its power source would have to last for an epoch, far beyond the radioisotope generators we use today. Its artificial intelligence would need to be completely autonomous, able to make decisions and conduct science without guidance from an Earth that would be light years away. It would be less of a probe and more of a robotic starship, sent on a one-way voyage into the Great Dark. Its mission would be to rendezvous with one of these primordial bodies, to land on its surface, to drill into its pristine 4-billion-year-old ice. What secrets would it uncover, buried deep within that frozen heart? It would analyse the isotopes of noble gases to determine the comet's exact birthplace, confirming whether it was born around our Sun or a long-departed sibling star. It would search for complex prebiotic molecules, seeking to understand the inventory of organic chemistry available in the young solar system. It might even find clues to the physical conditions of the protoplanetary disk, preserved like insects in ancient amber. Such a mission would be humanity's ultimate archaeological expedition, a journey back to the literal moment of our creation. Even without such a mission, the Oort cloud continues to shape our destiny. Every few 100,000 years, a star passes relatively close to our solar system. Its gravity percolates through the Oort cloud, dislodging a whole shower of comets, sending them cascading towards the inner solar system. These comet showers could dramatically increase the impact rate on Earth, potentially triggering mass extinction events. The very structure that may have delivered the water and organics for life to begin also holds the power to extinguish it. The Oort cloud is both our cradle and a potential executioner, a reminder of the dynamic and sometimes violent universe we inhabit. And what of the future? As our sun ages, it will swell into a red giant. In about 5 billion years, its outer layers will expand past the orbit of Earth, incinerating the inner planets. But the Oort cloud, in its distant majesty, will survive. The comets will be gently warmed, their ices beginning to sublimate, turning the entire cloud into a faint glowing sphere of gas, a ghostly nebula surrounding our dying star. For a time, these trillions of tiny worlds will be the last surviving remnants of the solar system as we know it. Eventually, as the sun collapses into a white dwarf, its gravitational grip will weaken. Many of these objects will finally break free, drifting away to become the next generation of interstellar travellers, future Borisovs for other solar systems to discover. They will carry the chemical legacy of our home across the galaxy, potentially seeding other nascent worlds billions of years from now. So, when we look up at the night sky, we are seeing only the brightly lit stage. The true theatre of our solar system is incomprehensibly larger and darker. Beyond the familiar planets, beyond the Kuiper belt, lies this immense, unseen sphere of influence, populated by a number of worlds that defies easy comprehension. 10 trillion frozen ghosts, patiently circling in the dark, the silent majority of our solar system. They are the leftovers of creation, the exiles from a planetary war, and the keepers of our most ancient history. The visitor, 2I/Borisov, was a revelation. It held up a mirror to our own solar system, and in its reflection, we saw the ghostly outline of this trillion-strong family. It taught us that our home is not an island, but a peninsula, connected to a vast cosmic continent. It reminds us that the line between what is ours and what is alien is far more blurred than we ever imagined. The universe is not just sending us messages, it is reminding us of a shared ancestry written in the composition of ice and dust. Out there, in the cold and the dark, a truly colossal number of worlds await. They are a silent testament to our violent past and a promise of the endless interconnected journey of matter through the cosmos. The wanderers from other stars are not strangers, they are simply family coming home. The ocean at the pole of inaccessibility is a void of liquid sapphire and absolute silence. Here, at Point Nemo, the nearest human beings are typically not found on any shoreline, but are instead the inhabitants of the stars passing 400 kilometres overhead. But in the year 2031, those inhabitants have long since departed. The great pressurised cathedral is empty, its corridors silent, its air recycled for the last time. The sky above this watery graveyard is a bruised purple, a twilight that feels heavy with the weight of impending history, indifferent to the mechanical drama beginning to unfold in the heights above. High in the thermosphere, where the air is so thin it exists only as a ghost of an atmosphere, a streak of artificial fire begins to tear through the veil. It starts as a flicker, a spark of jagged light that refuses to be ignored by the darkening horizon. This is the International Space Station, no longer a sanctuary of science or a testament to cooperation, but a falling monument of titanium and glass. For over 3 decades, it served as the only place where humans lived outside their terrestrial cradle, a fragile bubble of breath and thought suspended in the vacuum. Now it has become a doomed comet, a multi-billion-dollar architecture of ambition returning to the dust from which it was forged. Its silver skin, which once reflected the radiance of 16 sunrises every day, is now being licked by the first whispers of atmospheric friction. The internal systems, synchronized with the precision of atomic vibrations, count down the final 67 hours until the moment of impact. There is no one left within the modules to hear the hum of the cooling fans or the rhythmic click of the relays, yet the station remains hauntingly alive in its terminal phase. Its sensors, powered by the final desperate trickles of energy from the solar arrays, continue to record the physics of their own destruction. They measure the exact density of the upper atmosphere with a resolution no ground-based instrument could ever achieve, feeling the air thicken molecule by molecule as the altitude drops. They map the precise tilt of the magnetic field of the Earth, sensing the invisible lines of force that have guided the station through hundreds of thousands of orbits. Every byte of information streaming back to the surface is a sacred transmission, a digital testament to the final moments of a sovereign outpost. The station knows its own decaying velocity in a way that is purely mathematical and utterly cold. It understands that its forward momentum, once its shield against the pull of the world, is no longer sufficient to defy the gravity of the planet below. It records the increasing heat on its leading edges, the subtle vibration of the truss as the first stray atoms of nitrogen and oxygen strike the forward modules like microscopic bullets. This data will never be read by a human hand within these walls, yet it flows downward in a continuous stream, a digital consciousness detailing the anatomy of a catastrophe. The structure is a sprawling complex of laboratories and living quarters, a labyrinth of interconnected cylinders that once represented the height of human engineering. Now, as it descends through the 280-kilometre mark, the geometry that once provided safety begins to work against it. The massive solar arrays, designed to harvest the energy of the sun, have become drag-producing sails. They catch the thickening air, creating a torque that twists the entire station. The docking latches, which held together modules from a dozen different nations, begin to groan under the mechanical stress. The station is no longer a singular, graceful entity. It is a collection of masses fighting a losing battle against the fluid dynamics of the high atmosphere. Below, the surface of the South Pacific remains undisturbed. The waves at Point Nemo move with a slow, rhythmic indifference, unaware that the pinnacle of human achievement is about to be buried in their depths. The sky continues to darken, the bruised purple deepening into a void black that mirrors the space the station is leaving behind. There is a profound loneliness in these final 67 hours. We spent decades and billions of dollars to keep this fragile bubble hovering in the vacuum, nursing it through solar flares, micrometeoroid impacts, and the slow decay of its own components. We treated every leak and every failing battery as a crisis of the highest order. Now, we watch as the cold reality of orbital mechanics reclaims its prize. Why does every byte of data still feel like a sacred transmission as the end nears? It is because the station is more than metal and wires. It is a witness. It has seen the Earth as a whole, without borders, wrapped in a thin, glowing ribbon of atmosphere. It has recorded the shifting of the ice caps, the bloom of plankton in the oceans, and the glittering lights of human civilization at night. Even now, as it prepares to break apart and vanish, it continues its duty. It translates the silent, invisible laws of physics into a language of numbers and graphs. It is the way we look back at our world from the outside, and its destruction is the closing of a great eye that has watched over us for a generation. As the 67-hour window begins to close, the station enters the lower reaches of the thermosphere. The heat begins to rise from a mere suggestion to a searing reality. The outer thermal blankets, which protected the astronauts from the extreme temperatures of space, begin to char and peel away. The station is shedding its skin, revealing the skeletal frame beneath. The light it emits is no longer reflected sunlight. It is the glow of plasma. The International Space Station is becoming a star, a brief and violent sun born from the friction of its own homecoming. The descent is no longer a slow decay, it is a plunge. The data stream becomes more frantic, recording the failure of secondary systems, the loss of pressure in the external tanks, and the final, agonizing screams of the airframe as it prepares to surrender to the abyss. The story of this falling monument did not begin with fire, but with a singular defiant act of creation on the frozen plains of Central Asia. On the 20th of November, 1998, the Baikonur Cosmodrome trembled under the weight of a Russian Proton rocket. This was not a weapon of war, but a carrier of a new dawn. Atop the pillar of flame sat Zarya, a name meaning sunrise. This initial module was a 19-ton masterpiece of pressurized aluminum and steel, designed to provide the first heartbeat of power and propulsion for a dream that many deemed impossible. As Zarya cleared the atmosphere and shed its fairings, it unfurled its solar wings like a newborn creature, marking the first permanent foothold in the silent vacuum. This was the era of the geopolitical miracle. Only a few years prior, the two superpowers had stood at the precipice of mutual destruction, their missiles aimed at each other across the polar ice. Now, the very engineers who had designed those engines of annihilation were collaborating on a laboratory for the benefit of all. The Cold War had thawed, leaving behind a world hungry for a shared purpose. The International Space Station became that purpose, a neutral ground where the friction of terrestrial politics was replaced by the shared necessity of survival in an environment that offered no second chances. The second piece of the puzzle arrived only weeks later, carried into the heavens by the Space Shuttle Endeavour. On the 4th of December 1998, the American orbiter chased Zarya through the darkness. Inside its cargo bay sat the Unity node, a connecting hub that would serve as the gateway for future expansion. The rendezvous was a display of supreme orbital choreography. Travelling at thousands of kilometres per hour, the shuttle crew utilised a robotic arm to pluck the Russian module from the void and mate it with the American node. When the latches finally engaged and the seals pressurised, the first two rooms of our new home in the stars were joined. This was the moment the cradle was left behind. For the first time, humanity had established a sovereign outpost that was not tethered to the soil of a single continent. It was a bridgehead into the infinite, a place where the laws of the land were superseded by the laws of orbital mechanics. This initial pairing of Zarya and Unity was small, a mere fraction of what the station would eventually become, but it contained the DNA of everything that followed. It was a promise that we could live and work together in the most hostile environment known to our species. As the years progressed, more modules were added, laboratories from Europe and Japan, robotic arms from Canada, and additional docking ports from around the globe. The station grew like a living organism, a sprawling skeletal structure of trusses and pressurized cans. It became a city in the sky, a place where the sun rose and set 16 times in a single day, and where the concept of up and down ceased to have meaning. The inhabitants of this outpost were no longer just Russians or Americans. They were the first true citizens of the cosmos, representatives of a planet that had finally learned to look upward with a single unified gaze. The engineering required to maintain this outpost was staggering. Every bolt, every wire, and every seal had to withstand the extreme temperature fluctuations of space, swinging from over 100 degrees Celsius in the direct sun to minus 100 degrees in the shadow of the Earth. The station had to be shielded against the constant bombardment of micrometeoroids and solar radiation. It was a machine of incredible complexity, a closed-loop system where every drop of moisture and every breath of air was recycled and monitored with obsessive care. Yet, the most profound achievement of the 1998 Genesis was not the technology itself, but the enduring spirit of cooperation it fostered. For over 2 decades, through terrestrial conflicts and changing administrations, the station remained a sanctuary. It was a place where science took precedence over sovereignty, and where the shared pursuit of knowledge acted as a universal language. As we watch the station descend toward Point Nemo in 2031, we are witnessing the end of that era, a final chapter for the monument that proved we could transcend our origins and build a home among the stars. The station was never truly still. To remain in the heavens, it had to master the physics of the perpetual fall. It was locked in a relentless race against gravity, a high-stakes game of velocity and momentum that defined every second of its existence. To understand why it eventually fell, one must first understand the delicate mathematical tightrope it walked for 33 years, maintaining a speed that defied the natural urge of every object to return to the Earth. This was the silent, invisible engine of the station's survival, a constant exertion of kinetic energy that kept the abyss at bay. The station exists in a state of perpetual paradox, a high-speed projectile that never finds its target. To remain suspended in the vacuum, it must satisfy a rigorous mathematical demand, the maintenance of a velocity so extreme that it defies the intuition of the terrestrial mind. This speed is 17,500 miles per hour, or 28,000 kilometers per hour. At this rate, the station traverses the entire diameter of the planet in less than half an hour, crossing oceans and mountain ranges in the time it takes for a human heart to beat a few thousand times. This velocity is not merely a byproduct of its journey. It is the very thing that keeps the station from being consumed by the world it watches. Gravity is a relentless master, an invisible tether that pulls every gram of the station's mass toward the molten core of the Earth. On the surface, this force is felt as weight, the firm pressure of the ground against the feet. But for the station, gravity acts as a centripetal anchor. It is constantly pulling the 450 tons of titanium and solar panels downward, attempting to drag it back into the thick, suffocating embrace of the lower atmosphere. Without its forward momentum, the station would drop like a stone, a catastrophic plunge that would end in a brief, brilliant streak of fire. However, because the station moves at 28,000 kilometers per hour, it possesses an immense quantity of kinetic energy. As gravity pulls the station down, its forward motion carries it so far across the horizon that the Earth's surface curves away beneath it. The station falls, but it misses the ground. For every meter it drops toward the center of the planet, the curvature of the Earth drops away by the same amount. This is the state of constant freefall, a geometric marriage between the pull of the world and the speed of the machine. The station is trapped in a circular path, a prisoner of its own velocity, forever chasing a horizon that recedes at the exact same rate it is approached. Within the pressurized modules, this physics manifests as the ethereal grace of microgravity. The astronauts do not float because gravity has vanished. At an altitude of 400 kilometers, the Earth's pull is still approximately 90% as strong as it is at sea level. They float because they, along with the walls, the air, and the very water they drink, are falling together. They are occupants of a container that is in a state of terminal descent, yet never reaches the floor. It is a world where the heavy becomes weightless, where a massive rack of scientific equipment can be moved with the touch of a single finger, all because the entire laboratory is surrendering to gravity at 17,500 miles per hour. This equilibrium is a fragile thing. The vacuum of space is not a perfect void, and the station must constantly fight to maintain the specific energy levels required for this delicate balance. Even at its orbital height, there are stray molecules of gas that strike the station's forward-facing surfaces. These microscopic collisions act as a subtle brake, a persistent friction that saps the station's kinetic energy. If left unchecked, this drag would slowly bleed away the velocity, causing the station to sink lower into the atmosphere, where the air is denser and the friction more punishing. This would initiate a feedback loop of decay, where loss of speed leads to lower altitude, which leads to more drag, until the perpetual fall finally ends in a collision with the atmosphere. To prevent this, the station relies on periodic infusions of energy, the reboost provided by visiting spacecraft. These engines fire to push the station back up to its proper height, restoring the 17,500 miles per hour required to keep the Earth's surface from catching up. It is a constant battle against entropy, a refusal to let the fall become a crash. For over 30 years, this dance continued without fail, a testament to the precision of orbital mechanics and the human will to remain aloft. The station was a silver needle threading the narrow gap between the vacuum of the deep dark and the crushing pressure of the world below, a high-speed witness to the laws of motion. As the station orbits, it experiences the world as a kaleidoscope of shifting light and shadow. It passes from the searing brilliance of the dayside to the deep, star-flecked ink of the night side every 45 minutes. This rapid cycle is a direct consequence of its immense speed. The station is moving so fast that it outruns the sun, witnessing 16 dawns and 16 sunsets in a single 24-hour period. Each transition is a reminder of the kinetic fire that keeps the station alive, a visual representation of the 28,000 kilometers per hour that separates the sanctuary of the modules from the terminal reality of the atmosphere. The physics of the perpetual fall is a reminder that stability in the cosmos is never static. It is a dynamic process, a constant expenditure of energy to maintain a position of grace. The station did not simply sit in the sky. It fought for its place there every second of every day. It was a projectile that had mastered the art of missing the ground, a monument to the idea that with enough speed and enough precision, even the most relentless pull can be transformed into a path of infinite possibility. But even this mastery has its limits, and the very air that the station once glided through would eventually become the instrument of its undoing. The vacuum of space is a convenient lie, a simplification taught to those who remain anchored to the ground. In reality, the boundary where the Earth ends and the void begins is not a sharp line, but a long fading exhale of gas that extends hundreds of kilometers into the darkness. At the altitude where the International Space Station resides, 400 kilometers above the crashing waves of the oceans, the environment is technically the thermosphere. It is a realm of ghosts, where the air is 1 trillion times thinner than at sea level, yet it is far from empty. Here, the station encounters a persistent, invisible resistance that defines the limits of its endurance. The primary inhabitant of this high-altitude wasteland is atomic oxygen. Unlike the stable oxygen molecules we breathe on the surface, which consist of 2 atoms bonded together, the oxygen at this height has been ripped asunder by the relentless bombardment of solar ultraviolet radiation. These singular, highly reactive atoms are a predatory species of gas. They do not merely drift. They strike the forward-facing surfaces of the station with the kinetic energy of a supersonic impact, fueled by the station's own 17,500 miles per hour velocity. This creates a phenomenon known as atmospheric drag, a microscopic but unrelenting friction that acts as a silent brake upon the station's momentum. This drag is the station's greatest and most constant adversary. Every second, billions of these stray atoms collide with the sprawling architecture of the outpost. While a single collision is negligible, the cumulative effect on a structure the size of a football field is profound. The station is a giant metallic kite, flying in a wind that is almost a vacuum, yet strong enough to steal its energy. This theft of kinetic energy manifests as a slow, agonizing descent. Without intervention, the station would lose nearly 100 meters of altitude every single day, spiraling inward toward a world that would eventually consume it in a flash of plasma. The massive solar arrays, which stretch out like gilded wings to harvest the radiance of the sun, exacerbate this struggle. While they provide the vital electricity needed to power the life support systems and the scientific racks, they also act as immense sails. They catch the thin stream of the thermosphere, creating a torque that the station's internal gyroscopes must constantly fight to counteract. The very components that give the station life also hasten its decay, a fundamental irony of orbital mechanics. The station, for all its technological arrogance, remains a prisoner of the very atmosphere it seeks to transcend. To survive this persistent drain on its vitality, the station requires periodic infusions of fire. These are known as reboosts, and they represent a critical lifeline from the world below. When the station's altitude drops to a critical threshold, a docked spacecraft, often a Russian progress freighter, an American commercial cargo vessel, or even the station's own Zvezda module engines, will ignite its thrusters. For several minutes, the silence of the vacuum is broken by the muffled roar of chemical combustion. These engines push against the direction of travel, restoring the lost velocity and lifting the station back to its safe haven of 400 kilometers. During these reboost maneuvers, the inhabitants of the station feel a subtle, ghost-like sensation of weight. For a brief window, down exists again. The coffee in a floating pouch settles toward one end. The loose cables along the walls sway with a newfound gravity. It is a reminder that their sanctuary is not a static fortress, but a dynamic machine that must be actively maintained against the pull of the abyss. These maneuvers are calculated with exquisite precision, ensuring that the station remains in its designated orbital corridor, clear of the debris that litters the lower altitudes and far enough above the thickening air to maintain its grace. Yet, this cycle of decay and restoration is an expensive and resource-intensive endeavour. It requires the constant launch of fuel tankers from the surface, a multi-million-dollar logistical chain that spans continents. Every kilogram of propellant burned in the high thermosphere is a kilogram that had to be fought upward through the dense atmosphere of the Earth. This dependency highlights the station's status as a managed ecosystem, a bubble of human intent that exists only because of a continuous expenditure of terrestrial energy. The atmospheric drag is a reminder that the Earth does not easily let go of its children. It reaches out with its thinnest, most ethereal fingers to pull them back. As the years have passed, the Sun has also played its part in this celestial tug-of-war. During periods of high solar activity, the Sun's radiation heats the upper atmosphere, causing it to expand outward like a balloon. This puffing up of the thermosphere increases the density of the air at 400 kilometers, significantly heightening the drag. During these solar maximums, the station must fight even harder to stay aloft, requiring more frequent reboosts and more fuel. The station is thus intimately connected to the cycles of the Sun, its very survival dictated by the temperamental outbursts of our local star. The invisible resistance of the air is the silent narrator of the station's history. It is the force that dictated the shape of its orbit, the timing of its missions, and the design of its modules. It is a testament to the fact that space is not a place of absolute freedom, but a place of different, more subtle constraints. As the station moves through its final orbits in 2031, the drag will no longer be something to be fought and overcome. It will become the final embrace, the hand that leads the monument of titanium and glass down from the heavens and into the waiting arms of the Pacific. But before that end, the station would first unlock the deepest secrets of the cosmos, using its unique position to peer into the very fabric of reality. High atop the integrated truss structure, perched like a silent sentinel against the backdrop of the deep black, sits the Alpha Magnetic Spectrometer. It was delivered to the station in the month of May 2011, during the final flight of the Space Shuttle Endeavour, marking a pivotal moment in the transition of the outpost from a feat of engineering to a premier laboratory of fundamental physics. This $2 billion instrument is a 7-ton behemoth of silicon, magnets and electronics, representing the collaborative genius of hundreds of scientists from dozens of nations. It is a sifter of starlight, a machine designed to catch the high-energy debris of the ancient cosmos before it is obliterated by the protective shield of the Earth's atmosphere. On the surface of the planet, the thick blanket of air serves as a vital barrier for life, but for a particle physicist, it is a frustrating veil. When cosmic rays, atomic nuclei and subatomic particles travelling at nearly the speed of light strike the atmosphere, they shatter into a secondary rain of debris, masking their original properties. By sitting 400 kilometers above the world, the Alpha Magnetic Spectrometer can intercept these particles in their pristine state, capturing the data of their journey across millions of light years. It is the only instrument of its kind in the vacuum, utilising a massive permanent magnet to create a field that bends the trajectories of incoming charged particles. By measuring the degree and direction of this curvature, the device can determine the charge, mass, and energy of every single cosmic guest that passes through its detectors. The primary quarry of this celestial hunt is dark matter, the invisible scaffolding of the universe. For decades, astronomers have observed that galaxies rotate far faster than the visible matter within them should allow, suggesting the presence of a mysterious, non-luminous substance that exerts a powerful gravitational pull. This dark matter is estimated to comprise more than 80% of the total mass of the cosmos, yet it does not emit, absorb, or reflect light. It is a ghost that haunts the fabric of reality. The spectrometer searches for the subtle signatures of dark matter annihilation, rare events where dark matter particles might collide and destroy one another, producing an excess of positrons or other exotic particles that the instrument can identify with exquisite precision. Beyond the mystery of dark matter, the detector hunts for primordial antimatter. According to the prevailing theories of the Big Bang, the birth of the universe should have produced equal amounts of matter and antimatter. In the laboratory, these two substances annihilate each other on contact, leaving behind only pure energy. Yet the observable universe appears to be composed entirely of matter. This profound asymmetry is one of the greatest unanswered questions in all of science. By sifting through the cosmic rain, the spectrometer seeks a single nucleus of antihelium or anticarbon, a find that would suggest the existence of entire galaxies made of antimatter hidden in the far reaches of the void. The scale of this undertaking is staggering. Since its installation, the instrument has analysed more than 200 billion cosmic ray events. Each of these events is a discrete moment in time where a particle, perhaps forged in the heart of a supernova or accelerated by the immense gravity of a black hole, zipped through the station's architecture. The processing power required to categorise and interpret this deluge of data is immense, requiring a global network of computers to make sense of the results. Every few seconds, the spectrometer records another high-energy visitor, adding another line to the digital ledger of the universe's history. This is the station as a cathedral of the intellect. While the modules below house the humans who maintain the machine, the spectrometer operates with a cold, mechanical focus, indifferent to the daily lives of the crew. It is a bridge between the human scale and the cosmic scale, translating the silent laws of subatomic physics into the language of human knowledge. The findings of the alpha-magnetic spectrometer have already challenged existing models of cosmic ray propagation and provided the most detailed measurements ever recorded of the electron and positron flux in our galaxy. It has turned the International Space Station into a vital outpost for understanding the very beginning of time and the ultimate fate of the stars. As the station continues its 67-hour descent toward Point Nemo in 2031, the spectrometer remains active until the very end. Its magnets continue to hum, its silicon trackers continue to fire, and its data continues to stream toward the surface. Even as the atmosphere begins to claw at the station's frame, the device is still hunting for that one elusive particle that might rewrite the textbooks of physics. It is a testament to the human urge to know, to measure, and to catalogue the infinite. The $2 billion investment was not just for a piece of hardware, it was for a window into the dark heart of the universe, a window that is now slowly closing as the station surrenders to the gravity of the world it was built to transcend. But the legacy of the station is not written only in the stars or in the cold data of particle physics. It is also written in the very flesh and bone of the men and women who called it home. While the spectrometer looked outward at the mysteries of the deep cosmos, the station itself served as a laboratory for a different kind of mystery: the resilience and fragility of the human body in an environment where gravity is a memory. To understand the future of our species among the planets, we first had to understand how the void transforms our biological essence, a metamorphosis that was documented in every heartbeat and every breath taken within the pressurized walls. The human form is a vessel shaped by the relentless pressure of a single planet, a biological architecture designed over millions of years to withstand the constant downward pull of Earth. When that vessel is transplanted into the weightless corridors of the International Space Station, it begins a slow and profound metamorphosis. The body, sensing the absence of the gravity that once defined its every movement, concludes that the very structures providing its strength are no longer necessary. It is a biological shedding of the terrestrial self, a systemic recalibration that begins the moment the engines fall silent and the state of perpetual freefall takes hold. The skeletal system, once the rigid scaffolding of the body, becomes a dynamic casualty of this new environment. In the absence of the mechanical stress provided by walking, standing, or lifting against the pull of the world, the bones begin to dissolve. The body initiates a process of resorption, where calcium is leached from the skeleton and expelled through the kidneys. Every 30 days, an inhabitant of the station loses approximately 1% of their bone density in critical areas, such as the pelvis and the lower spine. This rate of decay is 10 times faster than that of severe osteoporosis on Earth. The skeleton becomes porous, a fragile ghost of its former strength, as the body attempts to unburden itself of the weight it no longer has to carry. Simultaneously, the internal fluids of the body undergo a radical migration. On the surface of the Earth, gravity pulls the blood and interstitial fluids toward the lower extremities, a process the heart and vascular system are designed to counteract. In microgravity, this downward pull vanishes, and the fluids surge toward the chest and the head. This fluid shift causes the legs to thin and the face to swell, but its most concerning effects occur deep within the skull. The increased intracranial pressure pushes against the delicate structures of the eyes, a condition known as space-associated neuroocular syndrome. The posterior of the eyeball flattens under the weight of the shifted fluids, and the optic nerve becomes inflamed. For many who dwell in the station, the very act of peering into the infinite cosmos causes a physical degradation of the organs of sight, blurring the stars they travelled so far to observe. This metamorphosis is not merely structural, it reaches down into the very coding of life itself. The most comprehensive study of this biological revolution was conducted during the one-year mission that began in March of 2015, involving the identical twin astronauts Scott and Mark Kelly. While Mark remained on the surface as a genetic control, Scott spent 340 days aboard the station, subjected to the unique stresses of the vacuum. This experiment provided an unprecedented look at how the environment of space interacts with the human genome. The results were a revelation of biological resilience and vulnerability. Researchers observed that the telomeres, the protective caps on the ends of chromosomes that typically shorten with age, actually lengthened while Scott was in orbit. This strange, temporary reversal of the cellular clock was a response to the intense physical stress and the bombardment of cosmic radiation. However, more significant was the shift in gene expression. The body, sensing the hostile conditions of high-speed travel and increased radiation exposure, began to activate and deactivate thousands of genes in a desperate attempt to adapt. These changes affected the immune system, the way the body processed nutrients, and the repair mechanisms of the DNA. While most of these genetic shifts returned to baseline shortly after Scott's return to Earth, approximately 7% of his gene expression remained altered for months. The station had acted as a forge, its environment of radiation and weightlessness hammering at the double helix of his genetic code. This was a clear signal that the human body is not a static entity, but a highly plastic system capable of profound, though often taxing, transformation. The data gathered from the Kelly twins and hundreds of other residents of the station has provided the foundational knowledge required for any future journey to the red deserts of Mars or the icy moons of the outer solar system. The station served as a bridge between the biological certainty of the Earth and the terrifying potential of the deep dark. taught us that we can survive the transition, but not without a cost. We are creatures of gravity, and when we leave it behind, our bodies begin to drift toward a different state of being. The station was the laboratory, where we learned the limits of our own flesh, documenting the leaching of bone, the shifting of blood, and the mutation of genes with a clinical and necessary detachment. This biological data, like the particle physics recorded by the spectrometer, was a vital part of the station's sacred transmission. It was the record of our first tentative steps into a realm where we do not belong, a map of the physiological territory that must be mastered if we are ever to become a multi-planetary species. But survival in the vacuum required more than just the adaptation of the body. It required the creation of a closed mechanical ecosystem that could turn waste into life. Deep within the humming modules, a different kind of alchemy was taking place, a chemical reaction that allowed humans to breathe and drink in a place where nature provided nothing but a void. The mechanical heart of the station beats with a rhythmic chemical precision, performing a feat of molecular alchemy that defies the scarcity of the vacuum. This is the Sabatier system, a testament to human ingenuity named after the French chemist who first described its potential in the year 1897. In the hostile silence of orbit, where every litre of water and every breath of air must be hauled upward at immense cost, this system serves as the cornerstone of a closed-loop existence. It is a machine that transforms the very waste of the human body into the fuel for its continued survival, a cycle of renewal that has allowed the station to remain inhabited for more than 2 decades, without a single moment of total depletion. The process begins with the most basic of human necessities, the act of breathing. Every person aboard the station exhales carbon dioxide, a gas that would quickly become a lethal poison within the confined volume of the modules if left unmanaged. While chemical scrubbers initially captured this waste, the arrival of the Sabatier reactor in the year 2010 transformed this burden into a resource. The system takes the concentrated carbon dioxide and combines it with hydrogen gas, a byproduct of the oxygen generation assembly, which uses electricity from the solar arrays to split water molecules into their constituent parts. Inside the reactor, under intense heat, and in the presence of a nickel catalyst, these two waste products undergo a violent and productive marriage. The carbon and oxygen from the breath of the astronauts are stripped apart and recombined with the hydrogen to create 2 new substances, pure water and methane. The water is immediately reclaimed, filtered, and fed back into the life support system, where it can be consumed by the crew or split once again to provide fresh oxygen. The methane, a high-energy gas, is traditionally vented into the void as a glowing trail of discard, though its presence represents a potential fuel source for the future. This chemical elegance extends to every fluid within the station's pressurized hull. The water recovery system is a marvel of engineering that treats the station as a singular, living organism. It collects the humidity from the air, the evaporated sweat and breath of the inhabitants, and processes the urine of the crew through a series of centrifugal filters and chemical treatments. This reclaimed moisture is purified to a standard that exceeds almost any municipal water supply on the surface of the Earth. Within the station, the distinction between waste and resource dissolves. The coffee consumed in the morning becomes the water of the afternoon, a continuous loop of hydration that reduces the need for resupply from the surface by thousands of kilograms every year. The Sabatier system is more than just a survival mechanism for low Earth orbit. It is a critical prototype for the eventual colonization of the Martian surface. On the red planet, the atmosphere is composed of 95% carbon dioxide. By bringing a Sabatier reactor and a small supply of hydrogen to Mars, future explorers will be able to manufacture their own water and methane propellant directly from the Martian air. The station has served as the ultimate proving ground for this technology, demonstrating that humans can bring their own ecosystem with them into the dark, provided they possess the chemical keys to unlock the resources hidden within their own biological waste. As the 67-hour countdown continues in 2031, the Sabatier system begins its final cycles. The pumps that once moved reclaimed water through the labyrinth of pipes now slow as the power levels fluctuate, The reactor, which has hummed at several hundred degrees Celsius for years, begins to cool for the last time. The closed loop is finally being broken. The water that was recycled 1,000 times over will soon be scattered as a fine mist across the high atmosphere or vaporized in the heat of the descent. The chemical bonds that sustained life in the vacuum are being surrendered to the thermal energy of the re-entry. There is a profound dignity in this machinery. It represents a refusal to be limited by the harshness of the environment, a commitment to the idea that life can flourish anywhere if it is sufficiently clever. The Sabatier system was the bridge between the terrestrial cradle and the planetary frontier, a machine that proved we could live on our own terms among the stars. It allowed us to stay, to watch, and to learn, turning the station into a sovereign outpost of the human spirit. But as the station sinks lower into the gravity well, the elegance of chemistry must give way to the brutal physics of descent. The point of no return is approaching, where the grace of the orbit is replaced by the exponential violence of the air. The altitude of 280 kilometers marks a silent, invisible threshold in the architecture of the heavens. It is the point of no return, a mathematical boundary where the kinetic energy of the station is finally and irrevocably eclipsed by the thickening reality of the Earth's atmosphere. As the International Space Station sinks below this height during its final 67 hours, the nature of its journey undergoes a fundamental transformation. For decades, the air at 400 kilometers was a mere ghost, a collection of stray atoms that could be brushed aside with periodic reboosts. Now that ghost is gaining substance, manifesting as a fluid force that begins to exert a tangible, punishing pressure against the massive structure. The 67-hour window is a countdown of kinetic surrender. At 280 kilometers, the atmospheric density is no longer a negligible variable. It is a wall that the station is hitting at 17,500 miles per hour. The physics of this descent is governed by the law of exponential decay. For every kilometre the station loses in altitude, the air density does not merely increase linearly, it multiplies. The resistance grows with the square of the velocity, and as the station is forced into lower, denser layers of the thermosphere, the drag coefficient begins to climb at a terrifying rate. The station is no longer gliding through a vacuum, it is wading through a mounting tide of nitrogen and oxygen. The first sign of this transition is felt in the very bones of the machine. The sprawling truss structure, which spans more than 100 meters, begins to experience a phenomenon known as aeroelastic flutter. The solar arrays, those vast gilded wings that once harnessed the silent power of the sun, are now the station's greatest liability. They possess an immense surface area, and as they strike the thickening air they begin to vibrate. This is not the gentle hum of a functioning machine, but a low-frequency shudder that ripples through the entire complex. The air, once invisible, is now pushing back, and the station's internal gyroscopes, the massive spinning wheels that maintain its orientation, begin to scream as they reach their physical limits, trying to keep the station from tumbling. As the hours bleed away, the descent accelerates. The loss of altitude is no longer measured in meters per day, but in kilometers per orbit. Each 90-minute journey around the planet brings the station into a world that is increasingly hostile. By the time the station reaches the final 48 hours, the heat of the friction begins to manifest. The leading edges of the forward modules, such as the Columbus Laboratory and the Japanese Kibo module, begin to warm. This is not yet the searing plasma of re-entry, but a steady, inexorable rise in temperature that the internal cooling systems can no longer reject into space. The station is beginning to feel the first fever of its homecoming. The sensors, still faithfully transmitting their data to the ground, record a harrowing picture of structural stress. The docking latches, the complex mechanical interfaces that have held the various modules together through decades of thermal cycles and visiting vehicle arrivals, are now being subjected to torque forces they were never designed to withstand. The atmosphere is not a uniform medium. It contains ripples and waves of density, and as the station hits these patches at 28,000 kilometers per hour, it experiences a series of mechanical shocks. The entire 450-ton assembly begins to groan, a sound transmitted through the metal frames as the architecture of cooperation begins to buckle under the weight of the air. At this stage, the station has become a prisoner of its own geometry. The very complexity that made it a marvel of engineering now ensures its destruction. The asymmetrical nature of the station, the way the modules are clustered and the trusses extend, means that the atmospheric drag is not applied evenly. This creates a massive rotational force, a desire for the station to spin like a lopsided top. The flight control computers, exhausted and deprived of the fuel needed for major corrections, fight a losing battle to maintain a stable attitude. The station is beginning to yaw and pitch, its graceful silhouette becoming a chaotic, tumbling shape in the darkening sky. The final 67 hours represent the triumph of entropy over intent. We spent 30 years defying the natural urge of the station to fall, using every trick of physics and every gram of propellant to keep it in the light. But the atmosphere is patient. It has waited at the edge of the world for 3 decades, reaching out with its thinnest fingers, and now it has finally taken hold. The air is no longer a ghost, it is a predator. It is stripping away the station's velocity, turning its immense kinetic energy into heat and vibration. The perpetual fall is no longer a state of grace, it has become a terminal plunge. As the station crosses the 250-kilometre mark, the data stream becomes a chaotic map of failure. Pressure sensors in the external tanks report rapid fluctuations as the structural integrity of the hulls is tested. The power from the solar arrays begins to fail as the vibration tears at the delicate silicon cells and the wiring harnesses. The station is dying, not from a single catastrophic event, but from the cumulative, exponential violence of the air. It is a monument that is being dismantled by the very planet it was built to study, a return to the terrestrial realm that is as inevitable as the setting of the sun. The stage is now set for the final, most violent act, where the architecture of the heavens will be torn asunder by the heat of its own speed. The atmosphere at 150 kilometers is no longer a suggestion of gas. It is a physical hammer striking the station at 17,500 miles per hour. At this depth, the International Space Station ceases to be a sovereign outpost and becomes a victim of fluid dynamics. The structural agony begins in the most expansive and fragile of its components, the 8 massive solar arrays. These gilded wings, which for 3 decades track the sun with the silent precision of a sunflower, are now caught in the mounting gale of the mesosphere. They were designed to harvest photons in a vacuum, not to withstand the blunt force of nitrogen and oxygen. They have become immense, unintended sails, catching the thickening air and generating a torque that the station's skeletal frame was never built to endure. The arrays do not simply break, they undergo a violent, shimmering disintegration. The thin blankets of silicon and polyimide film ripple and snap like flags in a hurricane. The beta gimbal assemblies, the mechanical joints that once allowed the arrays to rotate, are the first to surrender. Under the mounting pressure, the metal housings of these joints twist and seize. The long, delicate masts that supported the blankets buckle, folding back against the direction of travel until the tension reaches the breaking point. With a sound that would be a thunderclap if there were ears to hear it within the vacuum, the masts shear away. Fragments of golden foil and shattered solar cells are stripped from the station, trailing behind it like the luminous scales of a dying fish. As the arrays are torn away, the centre of pressure on the station shifts violently. The 450 tons of titanium, aluminum and glass begin to yaw and pitch with increasing ferocity. The central truss, the 300-foot backbone that holds the modules together, is subjected to a massive twisting force. This is the structural equivalent of a giant hand grasping the station at both ends and wringing it like a wet towel. The Z1 truss, the critical interface between the American modules and the main structure, begins to groan. The metal does not merely bend, it screams as the crystalline structure of the aluminum alloy is rearranged under the stress. The resonance of this agony vibrates through every bulkhead, a low-frequency shudder that marks the end of the station's integrity. the most harrowing drama unfolds at the docking latches, the common berthing mechanisms that have held the international modules together through thousands of thermal cycles. These rings of 16 high-strength titanium bolts were designed to maintain a perfect seal against the vacuum, keeping the precious atmosphere inside. Now, the torque from the tumbling station is trying to rip the modules apart at these very seams. The bolts, capable of withstanding tens of thousands of pounds of force, begin to stretch. The rubberized seals, which once kept the breath of astronauts from escaping, are compressed on one side and pulled thin on the other. Suddenly the first seal fails. A white fog of recycled air and frozen crystals erupts into the void as the internal pressure of the Destiny laboratory is vented in a fraction of a second. This explosive decompression acts like a rogue thruster, sending the station into an even more chaotic tumble. The metal surrounding the docking ports begins to peel back like the skin of a fruit. The screaming of the airframe intensifies as the atmosphere of the Earth begins to force its way into the gaps, a searing wind that is already beginning to glow with the first hints of plasma. The architecture of cooperation is now an architecture of ruin. The Japanese Kibo module, with its massive pressurized section and external platform, begins to pull away from the Harmony node. The bolts shear with the sound of rifle shots, their heads snapping off and ricocheting into the darkness. The station is no longer a singular entity. It is a collection of warring masses, each responding differently to the atmospheric drag. The European Columbus module, the Russian Zvezda service module, and the American laboratories are all being pulled in different directions by the invisible fingers of the air. The internal racks of scientific equipment, which once held the secrets of dark matter and bone density, are torn from their mountings as the modules themselves begin to deform. The glass of the cupola, the 7-windowed observatory from which humans looked down upon their world for 20 years, is now facing the direction of travel. The thickening air strikes the quartz panes with immense pressure. Though the glass is thick and reinforced, the frames holding them are being twisted by the agony of the surrounding structure. A web of cracks begins to spread across the central window, the very pane through which countless astronauts saw the curve of the Earth. As the station descends below 130 kilometers, the heat begins to climb toward the thousands of degrees. The metal, already weakened by the mechanical torque, begins to soften. The station is now a tumbling, incandescent wreck. The solar arrays are gone, the trusses are buckled, and the modules are beginning to separate into their constituent parts. The final 67 hours have compressed into a final few minutes of terminal violence. The sanctuary of science is being dismantled by the very laws of physics it was built to study. The metal is no longer screaming, it is melting. The titanium and glass are surrendering to the entropy of the descent, preparing to become a shower of molten rain over the South Pacific. In this moment of destruction, the station is no longer a tool of the human intellect. It is a testament to the cold, mathematical indifference of a universe that does not care for our monuments. The cosmos operates on a scale that renders the entirety of human history a mere rounding error in the calculus of the infinite. As the International Space Station disintegrates, its demise is not a tragedy in the eyes of the stars, but a simple, inevitable transition of energy. The vacuum of space is not a hostile antagonist. It is an absolute indifference, a silent medium that does not register the presence or absence of the pressurized bubbles we call home. The stars, burning with the fury of fusion for billions of years, do not pause in their slow, majestic cycles to acknowledge the loss of a few hundred tons of aluminum and titanium. To the universe, the station was never a sanctuary or a cathedral. It was merely a temporary concentration of matter, a brief anomaly in the overwhelming expanse of entropy. The laws of thermodynamics are the only true sovereigns of the heavens. They dictate that every ordered structure, from the crystalline lattice of a diamond to the complex architecture of an orbital laboratory, must eventually surrender to the mounting tide of disorder. The station's existence was a prolonged struggle against this fundamental truth. We spent 3 decades and billions of dollars to maintain a state of low entropy in a high entropy environment. We pumped energy into the system, recycled every molecule of water, and repaired every failing seal, all to preserve a tiny pocket of order against the inevitable. But the universe is a closed system with a long memory, and it eventually reclaims every debt. The descent into the atmosphere is the final audit, the moment when the energy borrowed from the Earth's chemical fuels is returned to the environment as heat and light. We take pride in our mastery of the Sabatier reaction, the chemical elegance that allowed us to recycle breath into water. Yet the universe has been performing far more complex transmutations in the hearts of stars since the beginning of time. In the core of a distant red giant, carbon and oxygen are forged in fires that would vaporize the station in a heartbeat. Our most sophisticated life support systems are but crude imitations of the elemental cycles that govern the birth of solar systems. We celebrated the mapping of dark matter with the alpha magnetic spectrometer, believing we were peeling back the veil of reality, but the dark matter itself remains unmoved by our observation. It does not feel the touch of our sensors. It does not acknowledge the 200 billion cosmic ray events we so meticulously catalogued. It simply continues to exert its silent gravitational influence, a ghost in the machine that has no interest in being discovered. The destruction of the station is a momentary flicker of heat, a tiny spark in a dark room that is quickly extinguished. The 13.8 billion years of cosmic history have seen the birth and death of entire galaxies, the collapse of stars into black holes, and the collision of worlds on a scale that defies the limits of human perception. In this context, the 67-hour descent toward Point Nemo is a microscopic event, a disturbance in the local atmosphere that will be smoothed over by the winds of the Pacific in a matter of days. The vacuum does not mourn the loss of the station's pressurized modules, nor does it celebrate the return of the titanium and glass to the terrestrial dust. It is a machine without a ghost, a sequence of causes and effects that proceeds with the terrifying precision of a clockwork mechanism. The silence of the void is not the silence of a grave, but the silence of a process that has no need for sound. When the docking latches scream and the metal twists, those sounds are contained within the thin skin of the modules, a desperate local vibration that cannot propagate into the vacuum. Outside, there is only the cold geometry of the descent. The station's trajectory is a line of code being executed by the gravity of the Earth. There is no malice in the atmospheric drag, no anger in the friction that turns titanium into liquid fire. It is simply the result of matter meeting matter at extreme velocities. The universe does not recognize the station as an achievement of the human spirit. It recognizes it only as a mass with a specific velocity and a specific drag coefficient. The human ego finds it difficult to accept this level of unconcern. We imbue our creations with meaning, seeing the International Space Station as a pressurized cathedral of shared intent. We view its end as the closing of a chapter in the human story. But the story of the universe is written in the language of mathematics, and in that language, the concepts of hope and peace are absent. There is only the conservation of energy and the increase of disorder. The station's kinetic energy, carefully built up by the roar of chemical rockets over 30 years, is being converted into thermal energy, which will then radiate away into the cold sink of the night sky. The books are being balanced, and the universe is indifferent to the identity of the debtor. The mapping of dark matter, the search for antihelium, the study of bone density. These were the obsessions of a species trying to find its place in the grand design. But the design does not require our understanding to function. The galaxies will continue to rotate, the stars will continue to drift apart, and the eventual heat death of the cosmos will proceed on its multi-trillion-year schedule, regardless of whether a pressurized cylinder of humans once orbited a small blue planet. Our mastery is a local phenomenon, a temporary flare of consciousness in a vast and ancient dark. The station's fall is a reminder that we are not the masters of the laws of physics. We are merely their subjects, bound by the same relentless equations that govern the farthest quasar and the smallest atom. Yet, even within this cold and mathematical reality, there is a reason why the 67-hour countdown feels like a sacred event. The universe may be indifferent, but we are not. We are the only part of this vast, unfeeling machine that has developed the capacity to look back at the gears and ask how they work. The station was our eye, a tool for the universe to witness its own complexity. Its destruction is the end of a specific way of seeing, a loss of a unique perspective that the cosmos itself cannot experience. We are the witness, and in our defiance of the cold indifference of the stars, we find the true meaning of our brief flicker of heat. This meaning is not found in the survival of the metal, but in the clarity of the vision we possessed while we were there. The persistence of the International Space Station was an act of profound biological and intellectual defiance. In a universe governed by the silent, unswerving laws of entropy, where life is a rare and fragile casualty of chemistry, we chose to construct a pressurized cathedral in the very place where breath is impossible. We did not build it because the vacuum invited us, nor because the stars required our company. We built it because the human spirit is a restless, inquisitive fire that refuses to accept the boundaries of its terrestrial cradle. This station was our declaration that the laws of physics are not merely constraints to be obeyed, but a language to be mastered. We spent 30 years maintaining a bubble of air and thought against the crushing weight of the infinite, just to earn the right to witness 16 sunrises and 16 sunsets in a single 24-hour cycle. This perspective, the ability to look down upon the curve of the world and see it as a solitary glowing marble in the dark, is the true legacy of the mission. While the universe remained indifferent to our presence, we were anything but indifferent to the universe. We watched the lightning dance across the clouds of the Amazon, the aurora borealis drape the poles in curtains of emerald light, and the city lights of humanity glitter like constellations on the dark side of the planet. These were not merely observations, they were the moments when the universe, through us, became aware of its own beauty. We are the sensory organs of the cosmos, the specialized cells that have evolved the capacity to translate the movement of atoms and the flow of photons into the currency of awe. As the station enters its final 67 hours and the sensors continue to stream their delta toward the Earth, we are witnessing the ultimate expression of this defiance. To a purely mathematical mind, the act of recording the exact atmospheric density and the precise decay of a doomed structure is an exercise in futility. Why measure the anatomy of a catastrophe that cannot be averted? Why catalogue the failure of a machine that will soon be a collection of molten fragments on the floor of the Pacific? The answer lies in the fact that we are the witness. We are the only part of the cosmic engine that can assign meaning to the data. By recording the details of our own destruction, we are not merely documenting a loss, we are completing the record of a journey. This data is the final transmission of a sovereign outpost that refused to go silently into the night. It is the way we look back at the laws of physics and say, "We saw you. We measured your strength. We understood the mechanisms of our own end." This is not futility. It is the highest form of human agency. We are the way the universe looks back at itself and asks how it began and how it works. Without a witness, the stars burn in a void of meaninglessness. Without a mind to perceive the curvature of space or the dance of dark matter, the cosmos is a play without an audience. The station was the front row seat, a precarious perch from which we could observe the mechanics of reality without the interference of the world below. The why of the International Space Station becomes clearest in these terminal moments. We care about every byte of data because we are the only entities in the known universe capable of caring. The vacuum does not care if the Sabatier reaction fails. The stars do not care if the alpha magnetic spectrometer falls silent. But we do. Our insistence on understanding the physics of the descent, even as the metal begins to glow with the heat of re-entry, is a testament to our refusal to be mere victims of circumstance. We are the architects of our own perspective. We transformed a hostile vacuum into a laboratory, a graveyard into a classroom, and a falling monument into a final, brilliant lesson in the nature of our world. The cathedral of titanium and glass is now a vessel of fire, but the knowledge it gathered is already safe, woven into the fabric of our collective understanding. The The data on bone density, the maps of cosmic rays, and the lessons of closed-loop survival have already been translated into the language of human progress. The station is surrendering its physical form, but it is leaving behind a map of the heavens and a blueprint for the future. We built it to see the sun rise 16 times a day, and in doing so, we learned that the light of the sun is less important than the light of the mind that perceives it. As the final orbits bring the station toward the bruised purple sky of Point Nemo, the transition from witness to memory is nearly complete. The 67 hours have been a long articulated scream of defiance against the silence of the void. We have mastered the Sabatier reaction, we have mapped the invisible scaffolding of the dark matter, and we have felt the genetic code of our own bodies shift in response to the stars. We have done these things not because they were easy, but because they were the only way to truly see where we are. The universe may remain indifferent to our departure, but it is a universe that has been measured, named, and understood. The witness is closing its eyes, but the vision remains. The final 80 kilometers of the descent are not a fall, but a transmutation. The air is no longer a gas, it is a searing white-hot forge that strips the International Space Station of its identity. The 450 tons of human ambition are now a singular, blinding streak of plasma, cutting across the bruised purple of the Pacific twilight. The titanium skin, once a shield against the absolute zero of the vacuum, now yields to the kinetic energy of its own homecoming. The station shatters into 1,000 incandescent fragments, a rain of molten jewels that illuminates the darkness of Point Nemo for one final, brilliant moment. The modules, Zarya, Unity, Destiny and Kibo, which were joined in the spirit of peace and cooperation, now part ways in a chaotic explosion of light and heat. As the fragments descend through the lower atmosphere, the heavier components, the massive docking rings, the engine housings, and the reinforced structural nodes survive the thermal agony. They strike the surface of the South Pacific with the force of 1,000 artillery shells, sending plumes of sapphire water into the air. The heat of the metal meets the cold of the abyss with a hiss that is lost in the vast oceanic silence. The International Space Station is no longer a city in the sky. It is a collection of jagged artifacts sinking through the lightless depths, descending 4 kilometers until they reach the silt of the ocean floor. Here, in the graveyard of the space age, the titanium and glass will return to the dust of the world, joining the fragments of the Mir station and the countless robotic freighters that preceded it. The silence that returns to Point Nemo is absolute. The bruised purple sky fades into the black of a night that no longer holds a pressurized sanctuary for our species. The sensors have fallen silent, the solar arrays have been vaporized, and the 67-hour countdown has reached its zero. But as the ripples on the surface of the water dissipate, the true nature of the station's legacy becomes clear. The metal is gone, but the data remains. The physical monument has been surrendered to the gravity of the Earth, but the knowledge it gathered is now a permanent part of the human story. We have learned how to breathe in the void, how to heal the body in microgravity, and how to glimpse the invisible scaffolding of the universe. We remain the witness. The laws of physics continue their silent mathematical dance, but they are no longer unobserved. We have proven that humanity can build a home among the stars, and that we can maintain our curiosity even in the face of cosmic indifference. The station was a bridge, and though the bridge has been dismantled, the shore it led us to is now within our reach. We have looked back at our world from the outside and seen it for what it truly is, a fragile, borderless miracle that requires our stewardship. The destruction of the station is not an end, but a transition, a necessary clearing of the way for the next great cathedrals we will build on the lunar surface and the red plains of Mars. Our role in the cosmos is to translate the silent language of the universe into the vibrant language of human meaning. Every mission we launch, every laboratory we build, and every byte of data we record is an act of defiance against the encroaching entropy. We are the way the universe looks at itself, and our journey into the dark is the only thing that gives the stars a reason to shine. The legacy of the International Space Station is a call to never stop looking upward, to never stop asking how we began, and to never settle for the safety of the cradle. If this chronicle of our falling monument and the science of the perpetual fall has resonated with you, consider becoming a permanent part of our mission to document the wonders of the cosmos. Our work is a shared endeavour to preserve the scientific legacy of our species and to tell the epic story of our place among the stars. By subscribing to this channel and supporting our efforts, you join a global community of witnesses dedicated to the pursuit of knowledge and the exploration of the infinite. Together we will continue to look back at the universe and ask the questions that define our existence. The station has returned to the dust, but our vision remains fixed on the horizon of the next frontier. Join us as we continue to explore the history of the universe